So thanks all for coming to SoftENG this week. I'm Tomkins-Tinch, a software engineer in the Kubernete lab, and I have a quick talk today about the package manager Conda. So it's something that's worth being aware of. I think it's useful, and it has the potential to make software, the software that we create, easier to distribute to the scientific community. And from the experiences within our group, Conda has really allowed researchers to get past the annoyances of installing software so they can focus on the science. So this is a tweet that popped up the other day. So scientific software can be difficult for researchers to use, and it harms reproducibility and future work if something is difficult to install and get up and running. So folks tend to spend a lot of time installing software, but that's not necessarily work. We all use software in the course of what we do, but often the process to get something running, especially for more wet lab folks in some of our labs, can be convoluted and prone to pitfalls. For Python packages, it can be easy, but if you have a binary, you either have to hope that it's available in your system package manager, whether that's RPM, Aptitude, Yum, Homebrew, or you need to compile it yourself. And for compiled packages, you have to make sure you have the right compiler installed, have to hope that the make files or other automated build scripts will run on your platform, and any libraries that it links against have to be present in the correct version. And compiling for different platforms can be its own adventure. And of course, dependencies can also conflict. So it would be great if there were a universal incantation to install a software package on any platform, whether Linux or a managed Linux system like the Broad's cluster, Mac OS, or even Windows. So Conda gives us that ability. It's a series of prepackaged Python scripts that run on Windows, Mac, and Linux, and serves as a package manager for software available from Anaconda.org, which is, as we learned yesterday, an S3-backed package repository. But it makes it fast and easy to install software so we can get on with our day. It's under active development, and in the last, I would say year or so, it's become stable enough to rely on most of the time. And it's really starting to gain momentum, especially in the sciences. So you may have heard of or used Anaconda, which is a Python distribution from the same company published creating Conda, Continuum Analytics out of Austin. And Anaconda includes Conda, the package manager, but also it comes with R and hundreds of other scientifically relevant packages. It's large and may have many more things that you need. And so Conda is the lightweight package manager component of that you can install only just that for a given project. So Python packaging used to be a mess, as I'm sure some of us remember. If you use Python, you're familiar with pip, the package manager that installs packages released from PyPy. And it's great. It's multi-platform, works well, but can be problematic for modules requiring compilation. So it can distribute some Python C extensions, but it doesn't really address distributing non-C binary dependencies very well or non-Python binaries. So that means you either need to install that you can install Python packages with pip, but for standalone binaries, you either need to compile them and install them separately, or hope that they're available from the package manager of your platform. So Conda isn't just for installing Python things. And distributing software comes down to building the software, so whether that's calling compilers or collecting files, and it also comes down to installing it. And so Conda addresses both of these points for Python packages and for binaries and for interpreted software in most common languages. So it can install pre-built software applications for Linux, Mac, and Windows, and it can automatically work out dependency graphs and install in isolated environments. So rather than installing each application at the system level, there are Conda environments, which mimic the Linux file system hierarchy. So there are bin, lib, opt, etc. directories. And if you've used Python virtual environments, it's a similar idea, where you can isolate your software and its dependencies from other things you have installed. So Conda environments allow you to have multiple versions of something installed concurrently on your system, and in doing so, you can avoid dependency conflicts. So you can ensure that you only have the software you need for a given project. That's also really helpful for reproducibility, because if you want to export the full state of an environment with all the software that's installed, you can do that with Conda, and it makes it easy to send a YAML file to someone else so they can get up and running with the same environment. And so because of that, it supports reproducible science. And since Conda environments are self-contained and don't install anything at the system level, there's no need to have administrative access to install a system. You can just download and go, which is really nice if you need to install software and run it on the Broad cluster. So one thing that makes Conda useful to researchers in the biological sciences is the BioConda channel. And so this is something that was relatively recent as of fall 2015. And it's a community-developed collection of software for Conda focusing on the biological sciences. And so it's grown quickly. The barriers to contribute are low. It's on GitHub. And so anyone who needs an easy-to-install package can submit an open source recipe. And the BioConda build infrastructure, which is built based on Travis, automatically builds each recipe for 32 and 64-bit Linux as well as Mac OS. And more recently, it also builds a Docker image via Quai and Mold for use in Galaxy workflows. And there's been a ton of growth. Over 2,100 software packages are now available through the BioConda channel from over 200 contributors. So chances are, if more than a handful of people use a particular application, it will be present on BioConda these days. So SAMtools, Picard, all the things that we use or include tend to be available. So this is a plot of downloads from last August. I tried to regenerate it today, but due to the S3 outage, their API is still down, unfortunately. And so there are a few packages that many people use, and then there's a really long tail of packages used by relatively few people. And so often the recipes for those programs have been contributed by the original authors or the one or three people who use a program. But SAMtools, BioPython, BCF tools are at the top, as well as common dependencies like libxml, Perl, and Java. And among all the BioConda packages, about 1/3 use R, 1/3 use Perl, and about half depend on Python. So if you've added those up, there are some overlaps. And about less than 10% use Java. So BioConda currently ignores Windows, just because most bio software doesn't target it. GATK is represented, but the package is only a shell script that copies in a licensed jar file. We'd love to actually include it, but the license, as we know, doesn't allow that. Cromwell is on BioConda, though. So another great Conda channel to source from is CondaForge, and it's an open source effort similar to BioConda, but rather than focusing on scientific software, CondaForge packages system software and general purpose applications. And so BioConda packages that depend on standard libraries and system packages also now depend on CondaForge things. So if a program isn't in BioConda, there's a pretty good chance it's in CondaForge. So this is great. You can install things for most platforms, and many things are available, but how do you get started? It's easy to install. The first step is to visit the Miniconda website. If you Google it, this page will come up. And from there, it's just a matter of downloading a shell script and running it, or I guess a batch file in Windows, or executable, rather. After that, you just have to set up BioConda and tell it to use Conda to use that channel. And the main documentation for BioConda is available on GitHub, along with a list of full packages that are available, or you can say Conda search for a given package. So during the first step, you configure it to use the channels you want to source from, and the order does matter. And so we'll source from them in order, with the last one being the preferred one. And then it's just a matter of checking to see if a package exists and installing it. And so you can easily just Conda search package or Conda install package. Making environments is similarly easy with the conda create command, and you just either name an environment or give it a path to install to. And after that, you can say source activate, and it will prepend the binary directory for the environment to your system path. And anything installed while an environment is active is isolated to that environment, along with all of its dependencies.
Question?
Yep.
Would you have a different package for your test environment, for example, or a debugging environment?
In terms of for development purposes or for distribution?
For development or testing purposes.
So I'll get into the workflow that we use for testing for Conda in a little bit. But you'd probably use the same package and then include tests in your recipe. But we'll get to that. So documentation is online too. If you Google Conda get started, there's also a 2-page Conda command cheat sheet. So Condas are great for installing software, but for people like us who create software, it's also a great way to distribute applications. So if something doesn't exist, it's easy to make a recipe for it. Python packages are trivial to add. There's a Conda skeleton command where you just say Conda skeleton pypy, then the package name, it will make the recipe for you. And then compiled packages aren't usually more difficult than the commands that you'd use to compile something manually. There are a few gotchas, so where BioConda pins to particular versions of Boost, Perl, GSL, and HDF5. So if you use different versions, that can be an issue, or need different versions. But for the most part, things just work. So a Conda recipe is a couple files, a YAML file that describes the metadata for a recipe, and it includes the package name, its version, source location, and other packages it depends on, as well as a few simple test commands. And then there's also a shell script, build.sh, that includes any commands that need to be run to compile the software package. So the build script is also responsible for copying executable files into the Conda environment, so into the bin directory, or symlinking them if it comes from a more complicated directory. And so here's an example recipe. This one's for BWA. And the metadata YAML file is on the left and the build script is on the right. It's really short, fits on a slide. And it includes the commands you'd run if you were to build it locally. So standard make, I don't know how, the color's kind of hard to see, but just includes GCC and the source package, and then it Conda automatically knows to run this build script. And it builds in one directory and then copies it to a separate new test environment where it runs the test command that you specify. And for BioConda, the test commands are really basic. They tend to just make sure that something can execute, only because the test environment that BioConda uses isn't really intended for super long-running unit or integration tests. And those are hopefully covered by the upstream repository for the application. And then if the test passes, it makes a tarball and uploads it to anaconda.org. And so if you look it up, this is the official build process. It reads the metadata, downloads everything into the cache, and applies any patches. So if there are some quirks to the program that you need to correct, you can have a patch that's applied. We've had to do that for a few applications on Mac OS. And then it makes a build environment, and builds everything, and then runs the build script, and then copies everything to the test environment. It also, after building, does some post-processing steps. And step 7 includes more magic than the statement lets on. So it inspects each binary built, and for each script added to the build environment sandbox, it looks at any of the paths that are linked against, and it will change them to link against libraries that are within the Conda environment rather than at the system level. And so it will also rewrite paths in scripts that are hard-coded, so they point to ones within the Conda environment. And usually that just works. So in Linux, it does some magic with the patch CLF tool, and on Mac, it uses the install name tool to change some of the links. So getting into testing, we've recently started dealing with Conda programmatically and including it more into our development workflow. And so for our viral NGS pipeline for viral genome assembly, Conda packages are built automatically after unit and integration tests succeed on Travis in our repo, and then they're uploaded to anaconda.org. And so we have a deployment hook that, after a test succeeds, generates a Conda recipe automatically based on our, like requirements.txt pip file, and we have another file for Conda requirements, and those are the same ones we use for our unit integration tests. And those are incorporated into the recipe we render. And then that recipe is then built on Travis, and if the build succeeds, then it's uploaded to anaconda.org. And so we have unit and integration tests of our own code, and then the Conda recipe itself includes some other tests, mostly just that the tools are able to execute, and some unit test work. But to keep it test time down, we don't run the full test suite. And then if the Conda build passes, then we also kick off a remote build in a different repository where a Docker image gets built. And so once we tag a release, about 20 minutes later, we have a Conda package that's installable, as well as a Docker image that anyone can put on.
Where would you insert secret credentials?
So with the Travis platform, you can encrypt secrets, and it's using a private key that's specific to a particular repository. And so on the command line on your local system, you navigate to your repository and say Travis encrypt, and then your secret, and then it will spit out the encrypted form, and then on the Travis platform, it will be able to decrypt it, but branches won't be able to, forks won't be able to, and you won't even be able to because the private key is specific to that repository. And as I mentioned earlier, one thing to note is that anaconda.org packages are on S3, so they were unavailable yesterday, and tests were failing left and right.
Sorry,
Oh, that everything is backed by Amazon S3. So tests were failing left and right yesterday due to the outage. So anyway, that's a super brief and hopefully not too rushed introduction to Conda. But the next time you need to install a piece of software or give something a try, you can see if it's available on Conda. And for scientific software, you can see if it's on the BioConda channel. And it works on the Broad cluster, so you can recommend it to others in your group who make use of the cluster. And if your program is in need of a new distribution channel, you should consider putting it available on Conda. You'll see expanded adoption, and your users will thank you, really. So that's all I have. Phil? Any questions?
Just thinking there might be some difficulties trying to get everything to work. Do you want to do it like local using internal compute farm?
There would be challenges with that.
Okay.
Everything that we work on is open, so it made sense to do it on Travis where it's visible. But
we do have Anaconda available.
Right. So there is an Anaconda.kit for the cluster. There's also, I think, maybe a Miniconda.kit, but Anaconda comes with Conda. So you don't actually have to install the Miniconda via the shell script, though if you want the latest version, you do, since the Conda.kit is a little bit, or the cluster.kit is a little out of date.
If you want it updated, just let me know.
Okay, that'd be great. Conda's also open source, so you can check out the code too. It's on GitHub. Thanks.
Okay, thanks, Chris. So what I was planning on talking about is sort of an internal tool that I had made for sort of a use case that I think is not uncommon here at the Broad, where people have sort of ad hoc jobs, in particular like analysts, computational biologists. Most of my group is actually computational biologists. And for a long time, Uzure was, or before Uzure, LSF, was kind of the way that people would run these kinds of ad hoc things at the Broad. And I was trying to sort of find something that kind of filled a similar role, but could take advantage of cloud resources. So just kind of give an overview of where I'm going with this. I'm going to start by explaining the problem that I was looking at, and sort of a very brief kind of looking at options that I saw. And then just kind of reviewing that problem statement a little bit closer, and then talking about sort of my approach to tackling it. So this is the problem. At the core of it, the simplest form of it is, I, as a user, have something that I want to run with some parameters. This should not be hard. This should be easy. We should be able to run things. But, I want to actually run a bunch of these. And I have a laptop. And I can't run this on my laptop, whether it be I'm going to run so many of them, or this needs a lot of memory, This is why we have a cluster. We need some sort of compute outside of just sort of a laptop. And this is schematically, like high performance computing. I kind of had this typical pattern of, you have a shared cluster that is a capital cost, people make an investment, it's this thing that's available. You have a globally accessible file system that all the workers can access. There's some, high bandwidth interconnect between those two things. Every piece of this thing is expensive. And, users are put into this work queue. They can share this shared resource. And it's, it has a lot of nice properties and actually had been successful for a very long time. However, we're now sort of in a period where cloud computing also has a bunch of orthogonal advantages while introducing different problems. In particular, the biggest advantage for sort of myself and my users is the elasticity. There's months where I run nothing, and there are months where I will burn through 5 CPU years. And when I burn those 5 CPU years, I generally want to do it in 2 days. And so, I kind of really want to be able to have a variable. I don't want to have a capital cost. And so, to like a big upfront investment. And so I would like to be able to use the cloud. And so, kind of looking at, there are some efforts that I've seen that were trying to create the HPC experience on the cloud. So Star Cluster was an open source thing that I used. Cycle Computing has a product that I kind of think of as Star Cluster for grown-ups. Star Cluster was kind of a little brittle for my taste. Cycle computing did a lot more engineering in a pretty serious effort, and sort of had this idea of cloud bursting. But I mean, it is sort of still an awkward thing that they're trying to do. They've got a different design space, and they're trying to apply a sort of solution that was designed for a different platform on it. Very recently, Amazon introduced a service, AWS Batch, and really the language that you speak in that is a Docker image, a command, some requirements, and some volumes to mount, and then it will, you can submit a batch job there. Similarly, Google has an offering that I think that is the basis of what Cromwell uses. This may actually look very similar to the previous slide. You provide an image, a command, some requirements. The only difference is kind of, they have a model in which you can specify some things to localize, and after you're done, things to export.
We actually, so batch is also incoming.
All right, so Cromwell will also support that. But let's go back to the problem statement. I have a command that I want to run with some parameters, and the reality is this, is this thing I put at the bottom. It's also probably not going to work because I just wrote this. This is, I'm actually running this to answer some scientific question. This wasn't, a software development project where I, ran it through my functional tests and it verified that everything worked the way that it was supposed to. No. I'm doing something terrible in the sort of dumbest way I can think of, and I just want to get this run. And it's probably going to fail. And the thing that's awful about, the thing that sort of rules these guys out is these guys are APIs. I need some way, I don't want to write another piece of software that's talking to an API. I need something that I can just kick off. So as a user, using any of these cloud services to get my work done, there's all these things okay, I need to somehow get my execution environment from my laptop to the cloud. And Docker actually addresses most of this, but how do I get my data there? How do I get my results back? There's some buckets involved. How many machines do I need to turn on? Maybe I have an idea of this. I've never run this before, so how do I know how many machines do I need? Just generally coordinate all this stuff. And the last one is one that especially dominates, I think, in the sort of research space, is how do I quickly debug and iterate on this? I know it's going to fail the first time, so how do I quickly get to that second time and third time and fourth time to quickly kind of just troubleshoot as I'm going through this? So the way that I view the solution, it has to have at least kind of two parts. I actually, we need first a submission tool, which is the thing that the user actually interacts with. There needs to be not just an API, but something that the user runs or directly interfaces with. And it must be easy to submit work. And, kind of taking the philosophy of, good design is you keep designing until there's nothing left to take away. So at its core, it should just be submit and sort of the absolute minimum that you can possibly specify and sort of take as much of the mental burden off of the user. And so part of that is I should be able to submit something without worrying too much about where data is located. If it's local, it should make it trivial for me to tell it, yeah, just upload that when you need it and pull it down when you need it. And likewise, because I need to be able to iterate quickly, all this copying and data being in different places, it's essential that I have the ability to aggressively cache. Now, one of the beautiful things about sort of batch compute is it's very amenable to caching. A lot of the things that we're doing in batch compute is taking something static, running something, and generating another static blob of thing. And that therein lies, it's very nice that you can cache those things, and that there's not actually sort of that many things that are in flight or transient. You tend to have a few large static assets. And then once things are done, this tool must be able to give me access to that. Orthogonal to that is somehow that tool needs to have an execution platform. And, it has to have a few properties in order for it to work well in the cloud. It must be resilient to intermittent failures because things on the cloud do fail. Docker images is kind of the most natural way of having an execution environment, both locally and remotely. Things like that. And both Google and Amazon offer those things. And I did something completely different. Because, well, Amazon's thing didn't exist, and at the time, I couldn't find Google's documentation. And this is really a story about my experiences more than a suggestion of what you should do. So I ended up trying out Kubernetes. And the general sort of way that my solution works is you start off by creating a runtime environment with all of your dependencies. You start a Kubernetes cluster, and Google actually makes this extraordinarily easy. That's probably the reason why I'm using Kubernetes, is because Google, you can start a Kubernetes cluster from the command line with absolutely zero knowledge. I had absolutely zero knowledge when I did this. So that's why I ended up doing this. And then I have my tool, Kubeque, which you use to submit the job. And then once you sort of have seen that things are kind of running, you can add an auto-scaling node pool, which is to say you tell Google that add to this cluster a pool of machines with this configuration, and it will look at the Kubernetes information and decide how many machines to make that pool actually instantiate for them. And then you wait for the jobs to complete, and then when you're done, you can shut down the cluster, and whether the cluster is up or not, all of the results have been now stored on a Google storage bucket, and you can download them whenever you want, also through the Kubeque command line. So just kind of backtracking, so Kubernetes was not one of the batch scheduling platforms that I mentioned. It's actually a much more open-ended system that was originally intended for running long-running services, so like deployment of websites, things where you want to deploy on a cloud, containerized applications. A huge amount of engineering efforts has gone into Kubernetes, and I feel like my happiness with Kubeque and STEM in part comes from being able to leverage the huge amount of work that they have put into building this. It's a really nice platform. I've enjoyed doing things where I can kill services on one node or kill a node, and it gently just migrates those containers that we're running over to some other nodes where capacity is available. And it's really kind of a nice platform to work with. Specifically, the Google, what is the K? It's like the container engine? Okay. Google Container Engine. Again, I knew nothing, and I was able to say, I could go into the Google console and click Start Cluster, and it says it takes about 5 seconds, and now I have a cluster. And I also just the front-end tools for navigating, configuring this thing, just in exploring, made it very easy. And so it was really a pleasant experience. And if you've ever tried to deploy a large cluster solution, you don't usually say pleasant experience. So I mean, I think this was great. It's like this really turned it from like a big, long investment into, this was something I was playing with in my spare time to just kind of see if this was a good idea or not. I think it's great that they have this as a platform and you can just try it out. Google Kubernetes, even though it initially targets long-running services, they do have some sort of support for batch jobs, and they have some documentation, and they have they have an API for submitting things. Again, all of their stuff is on the level of APIs and patterns, sort of recommendations, but I wasn't able to actually find a tool that would submit things, so I had to write Kubeque. And so this is what it does, it is just a command line interface to try and submit things to a queue, where that queue actually resides in a Google Data Store database. And at its heart, it's got one core command, kubeque submit, and you give it the command to execute. And there's some things that I'm hiding here, in that there's a configuration file that says what my default container was, and it says what project that all of my work should be running in and all of this. But the world where I'm in, most of the time, I kind of have an environment with all of my dependencies, and the thing that I'm iterating on is often some script that is just calling out to a bunch of libraries, doing some analysis. So here's an example where I'm submitting a command line. It's got this little caret here to indicate, actually, this is a file that may change, and actually upload this and download it to the worker node that receives it, that actually is going to execute this. And so, the actual script that I'm actually iterating on isn't part of the container. That's kind of coming in every single time it is needed. And in fact, all the files that are, and all the data that gets uploaded actually gets stored in content addressable storage, which I'll touch on sort of near the end if there's time. So a lot of the time, things get cached if they don't change. But making small source code changes. Yeah, Jeff.
Are you saying S3 generically there?
Yeah. I started off with S3 and Amazon, and at some point pivoted towards Google. So yeah, Google storage. Yeah, every time you see S3, just assume it's GS. But yeah, so it just kind of trying to make that workflow quick. So sort of a slightly different variation of that is here I'm uploading both a file, the original script, as well as a script that's a parameter. And here I'm submitting something where I've actually got a list of files that I'm uploading. This is just kind of a shorthand syntax. I'm still debating whether that's a good idea or not. In practice, it tends to be before too long you accumulate a bunch of files you want. So, you can list the files that you need there. But this is the thing that is actually probably the most powerful thing about this, is that you can say, here's a CSV file of parameters. And that CSV file, it takes each row in that file, and it creates a separate job where the parameters are filled in based on the values in that column. And so now I've taken something where I submitted one job, and now with a CSV file that has 100 lines in it, I can trivially submit 100 things, and they all run in parallel, and they're all tracked as a single entity. Now, this doesn't provide anything in terms of gathering those results, but this is a very common operation that we do where we want to sort of run the same thing, but just different parameters, and just do that scattering piece. That's actually the hard part often. Running the gather or collecting the results, is not that big of a deal, but just sort of the management of farming out 100 things and keeping track of their status, and for those that received, some node failed, like migrating those, that's really what this tool is targeting. And so it makes it trivial to be able to sort of farm out a large array of work. There's sort of one other note, like, some stuff so that I could not have to even bother uploading stuff, because sometimes if you have some large asset, it already exists out there. But that's the spirit of it. And so, again, getting down to the sort of idea of trying to distill, like, what a job submission tool needs, this is the shortest list I could get down to. So there's commands for submitting, looking at the status, when things are done, fetching the results, and there's a command for deleting or killing a job, like cleaning up if it's done, but deleting it, killing it if it's kind of in progress. And then likewise, there's kind of commands that are orthogonal to submitting work that are focused on managing the cluster and its health, such as starting and stopping the cluster, and then things about working with node pools. So, node pools let you could explicitly say, I want 10 machines, or you could say, oh, I want an elastic thing. You can say, oh, I want these to be preemptible to keep costs low, things of that nature. And, part of the thing that's been really valuable is, since this is built on Kubernetes, there's a huge amount of infrastructure or a rich ecosystem that I can rely on. So my tool has very simple things about, like, status and whether things succeeded or failed. But if you actually, or for instance, if there's something in my tool fails, there's the whole wealth of the Kubernetes interface. Like, this is the Kubernetes dashboard that comes out of the box. And, and it's collecting metrics like CPU usage, memory usage on a per pod basis, and exposing all of that where your job is running. Like, if there's any sort of actual details that you need, they're still accessible. My tool has been about trying to hide as much complexity as possible, but you can always just go around that. And actually, the tools that are provided by Google and Kubernetes are actually pretty usable on their own right. It's just that they have a lot of information, so they, I think, are potentially overwhelming at first, but are really quite well done. And so lastly, the sort of last thing I kind of feel like I thought would be worth talking about, since it sort of inspired some design decisions, is caching. in order to make this sort of an interactive thing, I needed to be able to move, the real problem I often felt like was moving data around. And so uploading data, it's the mode that I'm trying to encourage is doing things on your laptop, like editing files on your laptop, working with, having the data files on your laptop because you generated them. And so how do I as quickly go from your laptop to the cloud? And so this is handled by sort of multiple layers of caching. So at this very first thing is computing a hash of the data using SHA-256 so that I've got a nice long hash and don't have to worry about collisions. Yeah, Dave? Is that long enough? Yes. I don't remember, it's, it's kind of like, it's one of the, if you independent collisions, if you assume things are independent, sort of how many times in the universe, life of the universe, or, how many atoms, how many universes worth of atoms you have unique prefixes, or unique hashes. So, it's, I forget, I think SHA-256, I think is giving me a hash that's around, actually I can't remember. I almost want to say it's 256 characters, but that's not true. But I kind of did I did a sort of some looking. Git uses, Git uses SHA-1, but I think it uses hashes that are on the same order of length. But this is probably actually on the side of overly conservative. Yeah, 512 would be pretty crazy, but 512 bytes is small, so it's why not.
MD5 sum would work for something like that?
Yeah. So MD5 sum. That is now getting in the realm of. I wouldn't be surprised if I got a collision over a long period of time. It's like Dropbox, for instance. Dropbox. I don't know if this is still the case, but for a long time, Dropbox wouldn't actually send the file that you have on your drive initially. It would actually compute the hash. One of these long prefix hashes with the understanding that the probability of collisions is extraordinarily low, and only if this didn't exist would it upload this. And it kind of had this sort of weird property that people didn't like from a privacy standpoint, that if someone from a different account uploaded the file, it would actually say, oh, it's already there. I don't need to bother uploading it. So you could tell if someone had ever seen data before, and it was sort of a bit of a privacy leak. But I kind of had the attitude, that was the thing that convinced me that if you have a company that's solely built around storing data, and their entire business is on not losing people's data, and if they were comfortable with low probability collisions, I guess I can be too when I only have a few thousand files.
Dropbox was also comfortable poking around with your admin rights too.
That's true. Dropbox might not be the best example for a bunch of reasons, but it's just kind of, it is, I thought it was interesting that it is true that these are really long numbers, and getting two identical ones is unlikely, especially if you're not being malicious and intentionally trying to generate two that are identical. So in any case, because reading through a file and computing a hash is actually an expensive process for large files, it actually has a local database that's a little, I think it's a SQLite database, of local path to the key that it looks up is the local path of a file, and for that local file it stores the M time and the hash so that it can, as the cheapest test it can do, it can see it has the modification time change since the last time it checked the hash, so there's some caching of the hash that takes place. So if it's not already in the database or the modification time has changed, only then does it compute the hash. Then that hash is the thing that is used for the storage location, actually in Google. If something is not already there, that's the only time that it does the upload. On the remote worker side, it downloads to a staging area, and again is using that hash for the name. And this is what content addressable storage refers to. If you have two files that have the identical content, then one version of it is getting stored because the name, the content is the key that is used to find the data. And so it kind of doesn't matter if you have 1,000 things that are actually the same content. It just, one of them gets uploaded, and that name can then be used as a key to look up in a cache from that point on, and it's a stable thing. So from that staging area, the file is either linked or copied to the target area with the target name that it's needed for. And this is nice because the fast path of you just make a small incremental change is, first, it looks up in the local database, it sees, okay, this huge data file actually hasn't been changed. Okay, it's still going to be stored in the same Google storage location. It checks, it's there, I don't need to do anything. On the remote side, it pulls it down, but before it even gets that far, when it goes to pull it down, it sees, oh, I've still got it in the staging area. I don't need to download it there either. And so the only step that it does is that last linking to the target name. The thing in practice that does not work well for is it's linear in the number of files. So my use case happens to be in one in which I tend to have like 5 or 6 data files and maybe 30 source files. And it does that very fast. But the reality is, like, if I had a massive tree, that would become slow, and I would need to start doing things that are more sophisticated, probably working on, hashing of trees and things of that nature. But for like a pile of scripts and a bunch of data files, it works beautifully.
Phil,
Yeah.
What about teams of people working together? Like use the same reference metadata or something like that. Is there any? Is everyone individual?
So for that, I guess I would have, say, one of two things. One, it would make sense if you really have stable reference data that you could just upload that into storage and use those names directly instead. Alternatively, if there's nothing to stop you from having a pool of people all using the same Google storage caching area, and then the first person that uses some data set would be the one to upload it, and everyone else would it would be there and no one else would need to pull it. And so with that, just kind of touch on the conclusions. So what I learned from this was that the real gap in this whole thing was there were ways to run batch jobs on the cloud. There just doesn't seem to be a command line tool to do it. So I probably didn't actually need to sort of build the stuff on top of Kubernetes that I did, which was the piece. I suppose I didn't really talk about it, but there is a piece that is the thing that is, there's a work queue that stuff is going into, and so there's a little thing that runs in Kubernetes to pull stuff down and localize the files, and then when things are done, push them back up. And so I did kind of reinvent what Google's pipeline thing does and what AWS doesn't localize. But I did kind of reinvent that, and perhaps I didn't need to, but on the flip side, it did give me more control. Like, one of the things I think with the pipeline, Google's Jess thing, API is that it spawns a VM for each task that it's executing, and I don't really know how long that takes or if that's an overhead. But in mine, I decided,
It's a few minutes.
It's a few minutes. So in mine, I kind of was comfortable with reusing a VM. So mine, I actually start a VM and it pulls from the queue and then starts running locally. And then as soon as it's done, it checks the queue again and starts over again. So there is no spin up and clean down. And it's true that runs the risk that one job could pollute something for a future one. But I was much more interested in getting quick turnaround than I was on, things being absolutely deterministic.
And that has actually been a feature request for Google Pipelines API and Batch as well, for that reason you see multiple jobs in a row say that, no, it makes no sense to allow that to even be a feature.
Mm-hmm.
So, you're onto something. This is what some people want.
And so Google Cloud Engine was very nice. It was also surprising to see that it's actively evolving. Like, as I was using it, there was a point where I paused because there was a feature I wanted, and then I came back a month later and that feature was there. So it is an active thing. And using Kubernetes is also very valuable in that there's a huge amount of work that is not batch computing that is nice to be able to tap into. I especially loved that I did absolutely no work to do anything about monitoring. Like, all of that just came out of the box. There is a big, rich thing of infrastructure that they have to collect output and to collect you know, metrics and things that you can already hook into that exist. And then lastly, aggressive caching was totally worthwhile, like being able to just sort of submit 2 jobs in a row and just have my one script that had a 3-line change upload and then immediately start executing just made everything worthwhile. In practice, it tends to be like starting up the cluster takes about a minute and getting the Docker image pulled down and a node all there. But then once I've sort of done one round, making incremental changes is trivial and fast and has been really much more pleasant to work with. So it kind of, you know, simulates that good old experience of being on a shared file system and being able to just tweak a script and rerun. And so it's been kind of useful. So with that, thanks everyone.